So let's go over this acid-base test. Okay, so I gave you a little scenario up top, and I said that HClO is a common disinfectant that's used in public water supply. It's also the active ingredient in Clorox, except in Clorox they'll call it sodium hypochlorite. In any case, a solution is prepared of this H in front acid by adding sodium hypochlorite to water. So I'm asking you to write the net ion equation for the preparation of that from sodium hypochlorite and water. So you should have started with sodium hypochlorite. Now, sodium hypochlorite, all right, is of course part of that is a group 1 ion. So if you've got a group 1 ion, that is completely soluble. So we're never going to write the Na with this guy because anything that is soluble or completely dissociates acid or base cannot be written in that ion. This sodium is going to come off and it's going to float around the solution. And so we don't write it on both sides. Water we must write together because water is a terrible electrolyte. Now when I say electrolyte, I mean sodium hypochlorite is a very good electrolyte because of the solubility of the Na, because it's a big ion, it's +1, its Coulombic attractions are low. It's going to break apart into Na plus and Cl negative. And the more free ions you produce, the more you conduct electricity. So basically, I'm going to change my conversation to being soluble or dissociating is to becoming a good electrolyte. So water is a terrible electrolyte. It doesn't conduct electricity, so I write it together. So essentially, the water and the chloride ion are what are part of, or what is reacting here. So in any case, ClO becomes HCl because I say I'm preparing, I'm making this. So it must be that H is giving and acting as an acid, the hypochlorite ion and H plus, and there we form the acid. Now when the water gives off an H plus, it makes the hydroxide. So that's how this came. Now I would definitely accept it if you just wrote a proton here except instead of the water, okay, I accepted that. Of course, there's no hydroxide there. So I did accept the idea that if you just put the H plus instead of the water and then just made that, I did accept that. But letter B, you should be able to figure out who the acid and bases are. This is a base because it's accepting a proton. This is an acid because it's giving it, all right? And of course, here's the base, it's conjugate acid-base pair. So again, I don't know where people got lost here. I know it's worded in a way you have to think about, but you really spend some time thinking about what the wording here is. But I was preparing this, okay, this acid from the hypochlorite ion. All right, any case, the next part of this, the quality control chemist, in this case it's me, adds some solid hypochlorite ion to prepare the solution to be added to the water supply. All right, well, write a net ion equation for the reaction between HClO and barium hydroxide. And by the way, you should be using your graded test to review this, all right, to see this. I know you have the hard copy, but we're going to have the voice, the Grodsky, the person behind the scenes, okay, spending all this time preparing this for you. Okay, so again, barium hydroxide, you should know it's a strong base. How do I know? Group 1 and group 2 ions. The group 1 are called the alkali metals. The group 2 are the alkaline earth. Both those words mean bases, which means they're going to be soluble, which means this is going to produce hydroxides, free hydroxide. It's going to be a strong electrolyte. So I don't write the barium here. No, just the hydroxide ion because the barium is going to be free and it's going to stay as a conjugate, well, as a spectator. Strong bases produce the conjugate acids, in this case barium plus, that are terrible at pulling apart or ionizing water. So for the same reasons, sodium is soluble, so is barium, okay? Or for the same reasons, the sodium doesn't ionize, so does barium. Now barium is +2, it is, okay, more charged, but it's still able to act as a strong base, therefore it has no ability, the barium +2, to ionize water. So in any case, I'm starting with what? The reaction between this and this. Here's my acid. Now I do write this as a combined compound. I know the H plus can come off, but you should know this to be a weak acid. All right. Now, what kind of clues do I give you that's a weak acid? I gave you the Ka. Hello. It's so gosh darn small. And what is Ka again? Ka is nothing more than Keq, and basically a way for us to describe who's favored equilibrium, products over reactants. So if the acid, breaks apart to H plus and A negative, what you're going to have is, if you're not good at breaking apart and most of this stays together, you're going to have a lot more reactants, a lot more denominator, and a lot less of the products, the numerator. Therefore, this is going to be a very small number with a small numerator and a big denominator. Okay, and that describes this weak acid. So that is something that you should have been able to figure out. All right. So weak acid stays together. The what? Strong base drives the reaction forward by pulling the what? Pulling the H away. Okay. So this is losing the H. It's acting as an acid. This is a base, and of course you make the ions. Notice water is a terrible electrolyte, doesn't break apart very easily, therefore it stays together. So these are simple, but you got to think about the things that you have to keep together. All right, the barium was going to be the spectator. Okay, number 3, and the letter D was much like we did before in the previous worksheets. I wanted to know what the concentration of the acid, which by the way was, and this is what's got a lot of people, they couldn't figure out whether adding acid or adding base. So when you read this, look what it says here. 45 milliliters of my acid, the H is in front to tell you that, is added to a dry clean flask and titrated with barium hydroxide. It was titrated with. The thing that's titrated with is called a titrant. Okay, and that's the substance we're adding. That's why I have this drop of Jupiter, or this drop of goodness, which is the hydroxide, the base. Yes, we're dropping the base here. Okay, onto the what? The weak acid, because I added this to a dry, and I'm titrating the base. Okay, and I'm titrating with this base for this compound. All right, so you've got to be able to figure that out because people got this all backwards. Okay, so I'm adding a standard base to this acid. All right, any case, that being said, okay, they want to know the concentration of this acid that's in this beaker. All right, well, they're telling me that a total amount of the base is required to be added, to get to the equivalence point. And what's the equivalence point? For the millionth time, the equivalence point is where the hydroxides, or in this case, all right, this acid is equal to the hydroxides, or the H's that come from the weak acid. So like we did before, very simple, took the volume of the base, that was the titrant that was added. I know its concentration, and I find the total moles of barium hydroxide. Some people forgot that in one barium hydroxide, there are 2 hydroxides, so I have to times it by 2 to get the entire moles of the hydroxide. I'll say it again. You get the moles of the hydroxide by doing this molarity times liter like we've done a million times. But this time we had to times it by 2, just like our labs that we did. Okay. In any case, we get total moles of hydroxide. And then, of course, I go here. I divide by the what? The volume of the acid that's in my beaker. Notice the moles of the hydroxide that we got from the barium hydroxide, once we times by 2, equals the moles of the H pluses, because we're trying to find the concentration of the acid, divide by what's in the beaker originally. Okay, and most people did okay with that. This was pretty much a disaster here. Letter E was pretty simple. Find the pH at the equivalence point. Everyone knows that pH equals the pKa now because of the Henderson-Hasse block when you're at the halfway equivalence, because the log of the same number, same amount of conjugate acid and base, would give me a log of 0. So everyone mostly could see that from the other worksheets that we did, is that we took the negative log of the Ka to get my pKa. and my pK is this pH, okay, at the halfway equivalence. So when we draw this, and this is where it was disaster, we found that about 40 milliliters is what was needed to be added at the equivalence point. Notice my x-axis is the volume of the titrant. In this case, it was the base, the substance I add, that was added. Very important. So at 39 or 40, 39.97, whatever I have here, that's about 40 is the equivalence. Okay, so halfway would be about 20, right? So that's why we're at 20, and we know the pH equals the pKa at approximately 7.5. Now, some people got confused because, whoa, 7.5, that's close to 7. Who cares? Don't fall in love with the magical 7 number. In fact, we're never, ever, ever at a pH of 7, so don't worry about that 7. But that is the halfway equivalence, okay? So basically, I needed to know that we're starting with what? An acid. We were adding a base, so therefore your curve should went up. So you get a check for going the right way. You get a check for marking your what? Your halfway equivalence point with the right pH and right volume. And then you get a check for making sure that you are running through your equivalence point, but making it exponential. That's why it's a 3-check problem. Okay, going out to the back. And this is where it started falling off for a lot of people because I don't think you truly understand what's going on here. You're not taking notes, possibly. You're not reading into the things that I'm stressing. Okay? In the sketch, explain why your equivalence point was below, above, or at pH of 7. And I had maybe 5 out of the 40 some odd, I don't know, 35 or so, some odd AP Chem students I have get this right. Not enough. If it's above, this would be above 7, the equivalence point. And a lot of people said, well, it was a weak acid, strong base. So what? People said because it was a strong base that was added, that drove it up. No, 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 and no. The strong base is going to match the what? The hydroxides with the protons, okay? But what makes the pH go above 7 is the fact that in this case, we had a weak acid, HClO. And when the H was ripped off by the hydroxide because it was forcing it to happen, what remained was a conjugate base. And it sitting around in a large quantity, there's water around it, and this guy will take some of these H's away to produce some hydroxide. Okay? So again, you have to realize that if it was a strong acid and a strong base, and let me rephrase this, because not rephrase, but go back, because now you're remembering something. When I graded number letter C, so many people put H plus OH plus water. This is not a strong acid, strong base. You got to stop writing that equation. I told you in class, so many people will write that, and I would say, I don't know, 33% of the people wrote that here. Okay, this is not a strong acid, strong base scenario. Okay, some people said pH was equal to 7 here because that's what happens after a titration. Yeah, only for strong acid, strong base. You gotta get this down. Okay, letter H, calculate the final pH of the titration. Okay, that's just excess what? Excess, in this case, excess base that was added. We're going up. So from this point forward, how much excess base am I adding? So if I'm at 40 and it's going to 50, so what we did here, now it's not 40, it was 39.7, so I subtracted, okay, I subtracted the 10 milliliters, or in this case I subtracted 50 because that was a total volume here. 50 minus the 39.7, that gives me an extra 10.3. Convert that to liters, times it by the molarity of the base. That gives me the moles of barium hydroxide. I times by 2 moles of hydroxide. I want to convert to the concentration, so I divide by the total volume in the beaker now. Why is it 95 milliliters? Well, we added 50 to a beaker that originally had 45. I'll take the moles that I get here, divide by that, and I got my concentration. I do negative log. That gives me my POH because I'm after the pH. Minus from 14, my pH is 11.8. And you should have put that here and finished your titration, going to 11.8. All right, that was very much like what we did for our worksheet and or lab. So much of this, okay? Letter J, which of the following indicators the best choice for determining the endpoint? Well, because, and this is important, because my halfway point was 7.5, and because we're going up, you really needed something above 7.5. So that's why I could not accept anyone saying, oh, it's 7. No good, I will not accept that. It had to be the one that was very much above 7, because since the halfway was about 7.5, you needed something definitely above 7, where the equivalence point would be. Okay, and so the only thing way above 7 was the thymolphthalein. Now, justify your answer. You can say all of that, but basically, I need to just say that it's the closest pKa to the equivalence point. I had so many people say it was the closest to the end point. No, the end point is not what the graph gives. Remember, the end point is the color change that would help you stop to estimate the equivalence point. So many people put endpoint. I had to mark that wrong for your justification. It was the closest to the equivalence point. They are different. K was a disaster too. Explain why using an appropriate indicator would eliminate the need for a pH probe. Man, there's so many great ways to explain this, and I spend so much time in class. If you've got yourself a, I'm not sure what I just drew there, but if you got yourself, let's say, this kind of a deal right here. This probably should be more like this. Okay, I get that. My artistic abilities have dropped off here. Okay, so let's get rid of that. Boom. Now, if you've got this titration here, okay, if the endpoint or the color change of the indicator occurs, occurs a little bit above or below, and the rule is plus or minus 1 pH above the equivalence, right? Let's round this out a little bit. So if this is a pH of, let's say, 9, so maybe 10 is appropriate, or 11, because you'd still be on the asymptote. And some people said that very well, but not enough, okay? The point is, you can still use, as long as you use an appropriate indicator and the endpoint gets you somewhere close to the equivalence point, and it's a what? Close enough estimator. Notice we're all after the volume. So if this is a real asymptote, this endpoint would be, not much different than the volume at this equivalence point. So an appropriate indicator gives you a what? A great estimate of the volume needed to reach the endpoint. Okay, enough said. All right, so this was also a disaster, so you can expect to see this again. Now, what I did here for the letter L here is I basically took the conjugate acid and I took the base that was added, and I just said, hey, let's pretend I have 1 mole here. And because I said only 22 milliliters of the titrant, which was the what? The barium hydroxide, was added in this titration. If we go back to our graph, we can see that maybe. So when we look at our curve again, really important, okay, that we see that the pH equals the pK at this half equivalence point, which we figured out was 20 milliliters. So in the problem, they said they were at 22. That was after the halfway. Now, what does that mean? I'm adding hydroxides to acid. At this point, the conjugate acid and the conjugate base are the same, right? Really what this acid is ClO negative. And the conjugate acid is HClO. And we know at this point, this guy represents 100% of it, and there's 0% HClO. And we know that at this point, there's 50% of both of these, right? So as I move on this curve, there's less ClO and more of this. But eventually, at this point, these guys are equal. So past this point, as I drop more hydroxides, you're going to have a scenario where there's actually more of the conjugate acid. Okay? So therefore, this will be bigger than the conjugate base as we get past. This is halfway because at this point, there's going to be 100%, okay, of your conjugate acid, and there'll be 0% conjugate base. And so you should see that this is going down as we go through here. So being at 22 is important. I'm past this point. So I've got a little more of this. But if you don't see that, let's go back to the problem. I have a little stoich table that might help. So again, we're a little bit past half equivalence. So let's pretend I have a mole of the acid that starts in the beaker. Okay? And now I have 0.6 moles. Now, this would be 0.5 if we're at the halfway equivalence point, wouldn't it? And if this was 0.5, okay, that I added, originally there's none of this, this would be minus 0.5 because this is the what? Limiting reagent. This would be minus 0.5 and this would be plus 0.5 and that'd be equal. But I made this 0.6. Why did I make this 0.6? Because I'm a little bit past 0.5. That would be half of 1. So if I'm 0.6, this is still a limiting reagent, so minus 0.6, 1 minus 0.6 is 4, and look at this, I'd make 0.6. That's the key. Whatever I minus here, I would make of the base. So if this is 1 molar and I lose half of it, or I add half as much, I would lose half of this and make just as much as what I lost here, and they'd be equal. But having more of this past the half equivalence at 22, this would be a little bigger than 0.5, a little bigger than halfway, which means I'd make more of this and you'd lose more of that. And that's why the conjugate base is bigger than that because of that. And so all I needed to see here was that you'd have more conjugate what? You have more conjugate base here than the acid. I showed a couple breaking apart. And certainly there should be some sodium here that I didn't have, and some barium written in here as well. Okay, I wasn't even thinking in terms of those spectators. Thanks, Chris, for reminding me. So sodium should be here, and barium should be here as well because those are spectating ions. Okay, so hope that helps. I need you guys now to make sure you understand what you got wrong. You can look at this key without me talking, certainly, but now I want you to do a form below this. Okay, and the form will go over the same type of concepts, give you another place to practice. It's going to give you back the answers immediately, and it has a key, a handwritten key that's linked to it once you get the answers back. I'm working hard at this. I expect you guys to keep at it. Okay, you will get this. Hope that helped.